Hi guys, Mom Vici on the house. We'll now discuss combination. Another counting rule is combination. Here we count the number of experimental outcomes when our objects are to be selected from a set of objects using the equation that you are seeing on your screen. Let us be reminded that permutation depends on a specific order, like 1, 2, 3 is different from 2, 1, 3. Order matters. On the other hand, combination depends on a group of data or objects without depending on the order or sequence. So 1, 2, 3 is just the same as 2, 1, 3. We can order our sample points in a group or sample space and anyway, even randomly. For example, when we are given a menu, we see a list of food offered. But when we select our food, we can select first on the salads or pasta or even tea, even if they are listed at the bottom of the menu. Does it lower your bill if you do that? Of course not. That's why the order doesn't matter at all. Consider the sample problem here. The researchers of the five-member engineering team must be chosen to form the bioimagineering team. How many different bioimagineering teams could be formed? Order will not matter. It can be Maria, Lorna, Fe, or Lorna, Maria, Fe. So this is a problem on combination where n equals 5 and r equals 3. We substitute the values and you will be getting a value of 10 different bioimagineering teams that can be formed. The next example states that the bowl contains 6 M&Ms, 4 reds and 2 greens. If Mark randomly selects 2 M&Ms, how many different combinations can be selected? Again, order does not matter. There are 6 M&Ms, so n equals 6. With Mark selecting 2, so r equals 2. And substituting the values in the equation, we are getting 15 ways to choose 2 M&Ms. Suppose Mark randomly selects 2 M&M with exactly 1 green M&M. We do this in 2 steps. First, we select 1 M&M, so R equals 1, while N equals 2, since there are 2 green. Calculating for the number of combinations, 2 factorial divided by 1 factorial and 2 minus 1 factorial, the answer is 2. If we have already selected 1 M&M, this means that there is still 1 green in the bowl, so the total will be with 1 green and 4 red, we have 5. So n equals 5 and r equals 1. Calculating, we get 5 factorial divided by 1 factorial and 5 minus 1 factorial, and the result is 5. So the total number of ways to choose 2m and n with exactly 1 green is n equals 2 and n equals 5. And so by the mn rule, we have 2 times 5, and that is equivalent to 10 ways. Happens if Mark prefers that the two selected M and M should be exactly 1 green and 1 red. In the previous example, we take note that C of 2 and 1 is 2. We still need to compute for the 1 red. This will be our second step. There are 4 red in the bowl, so n equals 4, but we need only 1 red, so r equals 1. And substituting the values, we are getting 4. Again, with the m in rule, there will be 2 times 4 to choose 1 green and 1 red, or we have 8 ways. Now suppose Mark wants to know the probability that exactly 1 is red. Recall that the formula of the probability P of E is equal to ME over N, and we had already computed the values of 15 ways or total outcomes of choosing 2 M and M, and 8 ways of choosing 1 red and 1 green, meaning for the event to be exactly 1 red, the number of outcomes NE is 8, while the total number of outcomes N is 15. The probability, therefore, is 8 divided by the total outcomes of 15, and the result is 0.5333 or 53.33%. Finally, let us go to the game of cards. The first situation is this. A deck of cards consists of 52 cards, 13 kinds, each of 4 suits, spades, heart, diamonds, and clubs. The 13 kinds are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. In a poker game, how many ways can each player be dealt with 5 cards from a well-shuffled deck? In many poker games, its players dealt 5 cards from a well-shuffled deck of 52 cards. The deck contains 13 different ranks: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king, and 4 different suits: spades, hearts, diamonds, clubs. When dealing 5 cards to a player, the order in which the cards are dealt does not matter, so this is again a problem on combination. With n equals 52 cards and r equals 5, the combination is 52 factorial divided by 5 factorial and 52 minus 5 factorial. The result is 2,598,960 different combinations of 5 cards that can be dealt to a player from a well-shuffled deck of 52 cards. Now, suppose we want to calculate the probability of getting 4 of a kind in a 5-card hand. Thus, divide the number of ways of getting 4 of a kind by the total number of possible outcomes. So in step 1, to have 4 of a kind, we need to select 4 cards of the same rank: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, or king from the deck, and that would be 13 ways, 1 for each rank. But we need 5 cards, so we need to choose another card from what remained of the 52 cards. This will be our step 2. We have used 4 already, so the remaining card is 52 minus 4, or 48. And using the MN rule, the total number of outcomes that will be selected will be 13 times 48, equal to 624. Recall also that we had already computed for the combination of 52 and 5, and this is 2,598,960. So the probability is 624 divided by 2,598,960, and that is 0.0002401 or 0.02401%. Guys, we are only halfway of what needs to be learned. So on the next video, we will be discussing the counting rules, specifically addition rule. Again, please subscribe to my channel. And of course, please also hit the like button. Thank you.